Hello students, welcome to Sri Joyendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 11 of a unit work, power and energy. So let's begin with today's class. In today's class we are going to discuss about the collisions. Basically it is a part 3 of the collision, and in this session we are discussing the elastic collisions. If you remember the first session, we have divided into two segments. One is the elastic collision, another is the inelastic collisions. This is the segment of the elastic collisions. So let's begin with today's class. I hope you remember the previous classes. So let's begin with today's class. In today we are going to discuss about the perfectly inelastic collision. Do not get the confused that in the previous slide it was elastic, now it is inelastic. It has been said only inelastic, but it is in the category of elastic collisions. Yes, so it's a perfectly inelastic collisions, and we are going to discuss about the collisions in two dimensions. So let's begin with the first at perfectly inelastic collisions. So let's suppose the situation is that consider two bodies are there having mass m1 and m2, and they are moving with velocities u1 and u2, such as u1 is greater than u2, because we ensure that a collision must occur along a straight line undergo perfectly inelastic collision. So if it is the case of perfect inelastic collision, what we understand is that we have already discussed it in a previous sessions as well, that after collision they are going to behave as a combined body. They will be attached with each other and it will move as a combined body. So let understood they move with a common velocity v after the collision as shown in the figure. So if initially they were two separated bodies and after collision they are going to combine with each other, and if they are moving with certain velocity, then let's find out the common velocity v. So we can apply the law of conservation of linear momentum, and as per the law of conservation of linear momentum, m1 u1 plus m2 u2 can be written as m1 v1 plus m2 v2. After collision their final velocities would be equal, so it's a v1 is equals to v2 is equals to v. And if this is the case, we can have it's a m1 u1 plus m2 u2, that should be is equals to m1 plus m2 into v. So the common velocity could be calculated as v is equals to m1 u1 plus m2 u2 divided by m1 plus m2. I hope this is clear. Yes. Now let's begin and let's discussing with certain other parameters too. So what would be the initial total kinetic energy of the system? So initially they were both are moving with certain velocities, so their initial velocities and initial kinetic energy can be considered as it is the half m1 u1 square plus half m2 u2 square. Finally, final total kinetic energy of the system, it's in half into m1 plus m2 into v square. So this is the initial kinetic energy, this is the final kinetic energy, and this is the case. If this is the case, then the total loss of kinetic energy in perfectly inelastic collision. So when I say total loss, what I'm supposed to do is I'm going to have it's a kinetic energy initial minus kinetic energy final, because this will only give me the loss that initially I am having, and let's suppose 100 joule of energy, and after certain situation, in this case after a case of a collision, I have been left with only the, let's suppose, 40 joule of energy, so it is a loss of 60 joule. How does it arrives? Very basics, it's 100 minus of 40. So I'm doing the same thing, it's a total loss could be given as this is my initial energy, this is my final energy, and if I solve this, it will give me a delta ke, that is equals to half into bracket m1 plus m sorry m1 m2 upon m1 plus m2 into u1 minus u2 whole square. If if let's suppose the special case of this, if second body is at rest before collision, if second body is at rest before collision, then I must understand that u2 equals to 0, and if u2 equals to 0, That means my initial kinetic energy of the second body would be 0. So delta K, a change in kinetic energy, could be given as it's a half m1 u1 square into bracket m2 upon m1 plus m2. And if I take a fragments, if I take a fractions, it's a delta K by K initial. It would be an m2 divided by m1 plus m2. And if I take a ratio of the final energy to the initial energy, then it would be an m1 upon m1 plus m2. So this can be derived, this can be remembered as well. It depends on you that on which factors you depend. Yes, if you wish that no sir, I'm not going to remember this, then you must be ready with your derivation point part of you. But if you say that there is no time to derive, even you are correct, even you are correct that in examinations we are not having ample amount of time to derive the things, so you can go for the remembering part. I hope this is clear. Now one more and very important parameter is that let's look at this. This is m1, this is u1, this is m2, this is u2. They are going to collide, and once they are going to collide, they will be moving something like this. It's an m1 plus m2, and they are moving with velocity v. Yes, it is just this situation when they are going to combine. Yes, so what would be the value of coefficient of restitution? What would be the value of the coefficient of restitution? So what I can write is that E, that is the coefficient of restitution, was, it was the ratio of velocity of separation divided by velocity of approach. It is just the ratio of the velocity of separation to the velocity of approach. And when I say so, it's a velocity of separation divided by velocity of approach. So tell me, does this both the blocks separated or they move as a combined body? So your answer should be no sir, they are moving with the same velocity. So if they are moving with the same velocity, it's a v minus v divided by, probably it's an u1 minus u2. So but as this is v minus v, this will be the 0, because they are not going to leaving each other, they are work as a perfectly combined body. This is the case of perfectly inelastic collision. I hope this is clear. Is it clear? Is it any issues over this? Anything, any doubts, any doubts? Is there anything? No? So ready for the question? Have your pen, have your paper, and let's start your working. That let's suppose we have one wooden block, and this block is having mass m. This mass m is of 5 kilogram. Yes, we have one bullet which is of mass, let's say 100 gram, and which is moving with a speed of 400 meter per second. Yes, this bullet has been thrown, this bullet has been fired in the direction of mass m 5 kg. It has been embedded to this, and now a bullet plus this block has been moving with this, it's an m plus m. I need to find out this v dash. That the question is shown in the figure. As shown in the figure, find out final velocity of combined system. This is the requirement. As shown in the figure, find out the final velocity of combined system. So how will you do it? How will you do it? What could be done? So we understood that according to the momentum conservation, we understand that initial momentum should be equals to final momentum. And once I calculate initial momentum, that is equals to m1 v1 plus m2 v2, that would be equals to m1 plus m2 multiplied by v dash. So v dash could be, it's an m1 v1 plus m2 v2 divide by it would be the m1 plus m2. I hope this is clear. So let's calculate this. It's a v dash, that would be the m1 v1 plus m2 v2 divide by m1 plus m2. This mass m1 was of 100 gram. It's a 100 divided by 1000 because it is in gram. Velocity, it's a 400 meter per second. Plus second object, it's a 5 kg, but initially it is at rest. Yes, initially this was at rest. So when it is at rest, its velocity would be the 0. divide by divide by m1 plus m2, it's a 100 divide by 1000 plus 5 kg. I hope this is clear. So this is 1 2 3, it's a 1 2 3. So I have been left with the 40. This is 0, so doesn't make any sense. This has gone, this has gone. This is 1 by 10, it's a point 0.1. So this is 5.1. When I say it's a 5.1, I must understand that v dash should be approximately 8 meter per second. If I go for the actual value, then this v dash should be, this is the approximation, v dash should be somewhat lesser than 8, around 7.8 or 7.9 meter per second. I hope this is clear. So could it be done? Could it be? Can we do this? Can we do this? Yes, great. Now let's suppose I have been asked that in the previous question, find out loss of kinetic energy. So I have been not asked change in kinetic energy, I have been asked loss of kinetic energy. So what I need to do is I need to find out the initial kinetic energy of the system. So initial kinetic energy of the system could be written as half m1 u1 square plus half m2 into u2 square. The initial mass was the bullet, and its mass was the 100 gram. So it's 100 divided by 1000 multiplied by u1 square. Then that u1 could be written as, it's a 400, so this is 400 multiplied by 400 plus 1 by 2 into m2. The second object was the block which was initially at rest, so it's a 0 square. Now it is 1 2 3 4, it's a 1 2 3. Oh, I'm having only 3. So this could be written as it's a 400, so one have been left. And and the situation is, it's a 40 into 100. So this is, I have been left with this is, let's say, 2. It's a 200, this is 100, 2 is a 200 into 40, it's a 8000 joule. I hope this is clear. Is it clear that this 1000 has been cancelled by the three zeros? I have been left with 40, 40, 2s are 80, and 80 into 100, it's an 8000 joule. This was my initial kinetic energy. Now let's find it out that what was the final kinetic energy of the system. So I can have, it's a kinetic energy final, that would be equals to half into m1 plus m into v dash square. Yes, so when I say this, it would be an half into first block, it's an 100 divided by 1000 plus m, it's a 5 into v dash. Let's take an approximate value 8. So this has gone. This would be half into 5.1 multiplied by 64. This is equals to 32 multiplied by 5. It's this is 2, this is 64, this is 32. So this is equals to 32 multiplied by 5.1, which can be approximately it's an 160 around, approximately. It's an approximate, yes, if I consider this as a 5. So loss of kinetic energy, it's initially it was 8000 joule. Initially it was 8000 joule, minus of, if this is considered as an only 5 only, it's a 160. So the remaining is loss of the kinetic energy. I hope this is clear. What fragment would it be left? It's an 8000 minus 160. It's an 8000 minus of 160. Yes, it's a 7840. I hope this is clear. Is it clear? Is it? So can you do this kind of questions? Can you? Is it possible by you guys? Are you sure? Are you be ready with one more question? Are you? Let's do it quickly because clock is running very high. Let's have a look. That let's suppose a certain object is given. Let's have a diagram of it. This is M1 object which is having mass of 2 kg, which is moving in this direction with a speed of 4 meter per second. Another object is there. This is mass of M2. It is having mass of 4 kg. This is moving in this direction with a speed of 2 meter per second. Let's suppose they are going in this direction, and from here at this point they are going to be combined and moving with, after collision they behave as a combined system, and they are moving with the same velocity. I am interested in that velocity only. It's a v dash. So the question is shown in the diagram, as shown in the diagram. Find out combined velocity of the system. Shown in the diagram, find out the combined velocity of the system. So what I understood is that let's conserve the momentum. But when we conserve the momentum, we must understand that now they are moving in different directions. And as they are moving in different direction, I need to write it with respect of vectors. So what I understood is that my initial momentum of the system should be equals to the final momentum of the system. And while writing initial momentum is equals to final momentum, what I need to do is it's a 4 into 2 I cap minus of 4 into 2 j cap should be equals to a total mass. It's an I should write it's an m1 plus m2 into vector v. Is it clear? So this is 4 2s are 8i minus 4 2s are 8j. That should be equals to m1 plus m2. This is 2 kg, this is 4 kg, so this would be equals to 6 into velocity vector v. So this 6 into v should be 8i cap minus 8j cap. So vector v could be written as 8 by 6 I cap minus 8 by 6 j cap. That should be 4 by 3 I cap minus 4 by 3 j cap. So magnitude of this vector would be equals to root of, it's a 4 by 3 whole square plus 4 by 3 whole square. That should be root 2 times of 4 by 3. meter per second. This is the magnitude, and it will moving in the third quadrant. Yes, it is moving in this direction by combining. I hope this is clear. It was clear? Was it? Was it? No, I made a mistake. It is moving in the this quadrant. Uh, moving in this diagram. Yes, fourth quadrant. Sorry. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Great. Let's work for one more question. You are doing pretty good. Well done. Keep this. Continue. Let's suppose the question says that one of the object is here, and it is having a mass of 2 kg, and its velocity would be 10 meter per second in this direction. Another object is there which is having a mass of let's say 5 kg, and it is moving with a speed of 4 meter per second. These two are moving in this direction. They will now behave as a combined velocity, and they will move, let's suppose, in this direction. Find out the velocity. So the question says that find out combined velocity of the shown system. Find out the combined velocity of the shown system. So what I need to do is, it's an initial momentum should be equals to final momentum. So this is 2 into 10 I cap minus 5 into 4 minus of I cap. So this is minus I should be equals to it's a 2 plus 5 into vector v. But as I understood, this is 20 I cap minus 20 I cap. This is 7v, and so it's a v equals to 0 meter per second, because they have cancelled each other. I hope this is clear. So these are the questions, and basically from this kind of questions we can have a certain questions. I hope this is clear. Is it clear? Is it? Even we are going to do certain questions, but that will be done in the next session, because when we understood inelastic collision, it is better to do over there. So is it clear what perfectly inelastic collision is? Any doubts over there? Anything? Anything? No? Great. So let's now understand that what is collision in two dimensions. Yes, basically we are discussing this as the elastic collisions in two dimensions. So when we considered an elastic collision in two dimension, we basically discuss a one specific case of this elastic collision, because this case has been mentioned by the NCRT textbooks, and we are limited to that concern. Yes, so let's understood that what collision in two dimension is all about. We are talking about the elastic collision. So let's understood that this is mass m, which is moving with velocity u. This is another object having mass m, and initially let's understood that it is at rest, and now they are going to collide with each other. And after collision, let's understood that one of the objects, that is one of the mass, has been moving in this direction with velocity v2, and another object having mass m is moving in this direction v1, and they both are making an angle of theta 1 and theta 2 respectively with x-axis. So this is the situation. Now how should I deal with this? What could be what could be done? So what I understood is that every time momentum is conserved, even this is the same case here. So in elastic collision, momentum is conserved. So what shall I make a diagram? Shall I? It was m moving with u, another object m which was at rest, and the v1, the one of the object has moved in this direction, and this has made an angle of theta 1. Another object is moving in this direction, this is theta 2. So both are having same mass, it's a mass m, and this is mass m. So this is the situation. So what we are supposed to do is, that just convert them to their equivalent components. That if this is v1, this should be the v1 cos theta, that should be the v1 sin theta. Same way here, it's a v2 cos theta, this should be the v2 sin theta. Yes, so v2 cos theta, v2 sin theta, v1 cos theta, v1 sin theta could be there. So in elastic collision, momentum is going to be conserved, and according to the conservation of momentum along the x-axis, we can write it's an m into u, that should be is equals to m into u, that should be is equals to m into v1 cos theta 1 plus m into v2 cos theta 2. So from this, if I am cancelling this, it's a u is equals to v1 cos theta 1 plus v2 cos theta 2. So this is the momentum conservation along the x-axis. Now along the y-axis, when I consider along the y-axis, you will observe this, that initially I am not having any motion in the y-axis. So we can write it's a 0 plus 0. Yes, 0 plus 0, that should be is equals to, in this direction it's an m into v1 into sin theta 1 minus of m into v2 into sin theta 2. This is sin theta 2, this is 1, sorry, 1 and 2. Yes, so this is v1 sin theta 1 minus v2 sin theta 2 would be equals to 0. And from this is my relation 2. I hope this is clear. Now what we are supposed to do is, we are just going to square and add equation 1 and equation 2, because we are going to derive something. Let's have a look. Then it could be written as, it's an u square is equals to v1 square plus v2 square plus 2 v1 v2 into cos of theta 1 plus theta 2. And we understood that as the collision is elastic, applying law of conservation of kinetic energy, it's an half mu square, that could be written as half into m into v1 square plus half into m into v2 square. So this m has gone, and even this 1 by 2 1 by 2 1 by 2. So this u square is equals to v1 square plus v2 square. This is just the relation number 4. And if it is the relation number 4, just substitute the value of this u square in the equation number 3 that we have recently derived. So that would be v1 square plus v2 square, that should be equals to v1 square plus v2 square plus 2 v1 v2 into cos of theta 1 plus theta 2. Now if I write, it's this would be the cancel out, this v1 square, this v1 square, this v2 square, this v2 square, this has gone, and this is equals to 2 v1 v2 cos theta 1 plus theta 2, that would be equals to 0. From this it's a cos of theta 1 plus theta 2, that would be equals to 0. And if it is 0, then this could be written as cos of theta 1 plus theta 2 equals to cos of pi by 2 or 90 degree. So we understood that this theta 1 plus theta 2 would be equals to 90 degree. So the situation is, when two equal masses undergo an oblique elastic collision. When I say oblique, that means before and after collision they are not in the same line. Yes, here in this case, the after collision they are moving in the different lines. Yes, so undergo oblique elastic collision, they will move at right angles after collisions, if the second body is initially at rest. Does it clear? Are you sure? Anything that is not clear? Are you sure? Ready for the questions? Are you sure? Let's have a walk. Let's move on. So the situation is this body. This is having a mass of 5 kg, and it is moving with a speed of 20 meter per second. It is going to strike one more object having same mass. It's a 5 kg only, but initially this is at rest. After collision, let's say one of the body is moving in this direction, another is moving in this direction. So they have not mentioned the other angle, but this angle has been given. This is 30, and this is the velocity v1. Let's say this is velocity v2. So the question says find out value of v1 and v2 as shown in figure, as shown in figure. So you need to calculate the value of v1 and v2. What we can do now, first thing what we understand is that both are identical body, 5 kg 5 kg. One is moving with 20 meter per second while another is at rest. So if this is the case, then I must understand that this theta 1 plus theta 2 should be equals to 90 degree. Yes, they must be moving at right angles to each other, and if they are moving at right angles to each other, this is 30 degree plus this is theta 2, that should be equals to 90 degree. If it is the case, this theta 2 could be written as 90 degree minus 30 degree, and that would be a 60 degree. So it is the case of 90 degree minus 30 degree, which would be an 60 degree. So if this is 30, if this is 30, this should be the 60 degree. I hope this is clear. If this is 30, this is 60, so this theta 2 could be written as 60 degree. I hope this is clear. Now what we are supposed to do is that we are just going to conserve the momentum in horizontal directions and in vertical direction. So let's begin then for conservation of momentum. So let's write down, it's a conservation of momentum, conservation of momentum in x direction. So according to the conservation of momentum in x direction, so what I need to do is that this is the v1 cos theta 1, this is v1 sin theta 1, this is v2 cos theta 2, this is v2 sin theta 2. So according to the conservation of momentum in x direction, what I can have, it's a phi into 20, that should be is equals to phi into v1 into cos theta 1, it's a cos of 30 degree, plus phi into v2 into cos of 60 degree. So this phi into 20, it's an 100, that should be is equals to phi into v1 into cos 30, which should be a root 3 by 2, plus phi into v2 into 1 by 2. Yes, this phi has gone, so this is left with the it's a 20 is equals to root 3 by 2 v1 plus it's a v2 by 2. So this is our first relation, now next, it's a conservation of momentum in y direction. So when I conserve the momentum in y direction, in y direction, initially I am not having any motion in the y direction, so it's a 0 plus 0, that should be equals to, look at this is v1 sin theta 1, this is v2 sin theta 2. So that would be equals to phi into v1 into sine of 30 degree minus phi into v2 into sine of 60 degree. So this is equals to phi into v1 into sine of 30 degree, that should be is equals to phi into v2 into sine of 60 degree. So this has gone, sine 30, it's a 1 by 2, so it's a v1 by 2, that should be is equals to v2 into sine 60, it's a root of 3 by 2, this has gone. So I can have, it's a v1 should be equals to root of 3 v2. This is my second equation. So my first equation was that 20 is equals to 20 is equals to root 3 by 2 v1 plus v2 by 2. This was my first relation, and according to the second, it's a v1 that should be is equals to root of 3 v2. This was the second. So this was the first, this was the second. Let's put up the value and get it done. This is root 3 by 2 multiplied by v1. This v1 should be equals to root of 3 v2 plus v2 by 2. This should be a 20. So this is root 3, it's a 3 by 2 v2 plus v2 by 2. This is equals to 20. So this is 3 plus 1, 4 by 2. It's a 2 v2. This is equals to 20. So this v2 is equals to 10 meter per second. I hope this is clear. Is it clear? Is it? Yes. So v1 could be written as root 3 times of 10 meter per second. So when and when this kind of situation arises, I am having only one option. Yes, we have in reality, we have four unknowns. Yes, so I don't know v1 initially, we don't know v2, and we don't know theta 1, we don't know theta 2. But we have only in actual we have only three relations. Yes, one could be the momentum conservation, one is the coefficient of restitution, and another one that is of kinetic energy conservation. So only three relations are there and four unknowns are there, so it is not possible, it is just the impossible. So what they have given, what they will be given is that they will give one of the angle for sure, and once they are given one of the angles, once, so if one of the angle is given, second angle would be none to us in by directly, because we know that both are going to move at right angle to each other. So if one of the angle is given, second is indirectly given. So now only two unknowns has been left, one is v1 and another is the v2, and this two unknowns can be solved easily by the application of conservation of momentum only. That conserve your momentum in x direction, conserve your momentum in y direction, and yes, your task is over. I hope this is clear. Is it clear? Is it? So this can be done, this can be done very easily. Yes, only what you need to do is you need to make it a calculation. It is a bit lengthier, it may be bit lengthier, but we do not have any other options, so we are going to do it. It is as simple as that. I hope this is clear. Is it clear? Is it? So let's have certain questions over it. Let's have it. It says that a particle moving with certain velocity collides elastically with another particle at rest. Okay, if it were head-on collision, the kinetic energy transferred by the colliding particle is 100% when its mass is equals to, okay, so when the situation would be there, that when two identical bodies are there, or we say we don't know they are identical or not. So two bodies are there, one of the body is at rest initially, that has been given, and they said that if the kinetic energy transferred by the colliding particle is 100% when its mass is equals to, so what could be done? So let's take one of the example and you will find it that how this can be done. Let's understood that this is a body having a mass of 5 kg and it was moving with 20 meter per second in this direction. This was a body having a mass of 5 kg and it is at rest. It is at rest. They are going to collide elastically and they will move in this direction. Let's suppose this is the second body, this is the first body, this would be the second body, this is v2, and this would be the first body. So this is first and this is v1. So we don't know v1 v2, but what we know is that both are identical body. So we understand that mass of two objects when mass of two objects are equal and they collide, they collide elastically, they will exchange their velocity. I hope this is clear. Yes. So when mass of the two objects are equal and they collide elastically, they will exchange their velocity. So when they exchange the velocity, what I understood is v1, that this is having 20 meter per second, this is at rest, that means this is having 0 meter per second. So my first object will come to rest. And the second object must be having a speed of 20 meter per second. Yes, so their speed has been exchanged, and when the speed is exchanged, what I understood is that let's calculate the kinetic energy of first body initially. It is equals to 1 by 2 into 5 into 400. So this is 200, and this is equals to 200 into 5. It's 1,000 joule. Now let's calculate the kinetic energy of the same body after collision finally. Yes, it would be half into 5 into 0 square. So this is equals to 0 joule. So where this 1000 joule has gone? Where this 1000 joule has gone? Where is it? So if I see this situation very carefully, I will come to know that if kinetic energy of second body is initially, I calculate it's in 1 by 2 into 5 into 0 whole square, this would be 0 joule. Kinetic energy of second body finally, it would be 1 by 2 into 5 into 20 square. I hope this is clear. So this would be the 1000 joule. So in this case, kinetic energy first initially is equals to kinetic energy of second body finally, and the total energy has been transferred because initially this is having 1000 joule, and this body is having 1000 joules. So please do remember, two bodies are identical if two bodies are identical and one of them is at rest, then projectile will transfer 100 percentage of its kinetic energy 100 percentage of its kinetic energy to the target. Does it clear? Does it? So it will transfer 100 percentage of its energy. So a body which is moving with certain velocity is called as a projectile, and the body which is with which it is going to hit is called as the target. So here my first object is the projectile, this was projectile and this was target. Yes. So the question is, the kinetic energy transferred by the colliding particle is 100% when its mass is equals to the mass of the stationary particle. I hope this is clear. Is it? Great. Now the second question, it says that a heavier sphere moving eastward, it's in news. Okay. So heavier sphere moving eastward with a certain velocity v collides with a lighter sphere at rest. If it is perfectly elastic head-on collision, then after collision, okay. So it says that heavier sphere moves westward with same speed. Heavier sphere comes to rest. Lighter sphere moves eastward with a velocity of 2v approximately, and lighter sphere moves eastward with velocity of approximately. So what would be the situation? What could be the situation? Yes. So what we can do is that this is the heavier sphere. Yes, and this is the mass m1. It is moving in this direction with velocity of v1. This is the lighter sphere. Let's say it's a mass m2, which is initially at rest. It's a u equals to 0. Now now we are interested in this m1 and this m2. It's a final velocity v1 and v2. So here I am having an options of primarily on v1 and v2. So let's have a look that, and one more information is given that m1 is much greater than m2. Even this has been mentioned that m1 is much greater than m2. So what we can do, let's have a look that what can be done over here. That we know the relations of v1 and v2 in the very beginning. It was in the first session, first part of the collision. The v1 was, it's an m1 minus m2 divided by m1 plus m2 into u1 plus 2m2 divided by m1 plus m2 into u2. So if m1 is much greater than m2, what I can have is the v1 is equals to, I am going to ignore this because it does not have any effect. It's an m1 by m1, that is equals to u1 plus it's a 2m2 divided by m1 plus m2 into u2, as this was at rest, this is 0. So v1 should be equals to u1. Yes, and v2 v2 would be equals to, it's an m2 minus of m1 divided by m1 plus m2 into u2 plus it would be the 2m1 upon m1 plus m2 into u1. So the situation is if m1 is much greater than m2, if m1 is much greater than m2, then the v2 could be written as, let's understood that this is 0. Yes, second object was initially at 0, so this is 0 plus it's a 2m1 divided by m1, because this is negligible. It's a 2 into u1. So this is v2 is equals to 2u1, and this is v1, that is equals to u1. Now let's again check the options. So what this says, it says that my v1 will be moving with the same speed what initially it is moving, that it must moving with v, and this will move with twice of velocity of v. It's a 2 into v. So let's check it, the option that it says that lighter sphere moves eastward with velocity of 2v approximately. This would be the correct answer. I hope this is clear. Yes, these are very good questions, very good questions. I like this. I hope this is clear. Is it? So ready for the next question? Are you? Let's have a look. It says that a mass m1 moves with a greater velocity and it strikes another mass m2 at rest in head-on collision. It comes back along its path with low speed after collision. Then, so what does it say? It comes back along its path with low speeds. So this is the situation that a mass m1 was there. It is moving with a greater velocity. It's a velocity, let's say u1, and it strikes another particle which is mass m2, which was initially at rest in a head-on collision. That means it is going to hit it over here. It comes back. So after collision it is going to move in this direction, but with a lesser speed. Now when this will happen, so again this is the case, again this is the same case, what we have discussed over here, a certain with certain variations, that in this situation only the m2 is greater than m1, and the rest of the things are followed. So what you are going to do is that again I just give you the hint. Yes, again do the same thing, write down these things. Yes, so shall I write it down twice? Let's have a look. So the situation would be, in this case, it is just the hint, It is for the hint purpose only. So it's a hint for third question. Yes, it's a hint for third question. So in this case it was m1 greater than m2. Now in this case m2 would be much greater than m1, and again you are going to derive the v1. Again you are going to derive the v2 and take your decision. This is try yourself question. Yes, you are going to do this because we have already did one of the question based on same concept. I hope this is clear. Is it clear? Great. Try it yourself. Next, the collision in which the relative velocity is zero after collision. Yes, after collision the relative velocity is zero. They are perfectly inelastic collisions. Both the objects are static, such moving with the same speed in the same direction. I hope this is clear. So it is perfectly inelastic. Great. Let's move for the next question. It says a body of mass m moving with a constant velocity v hits another body of same mass. Great. Moving with the same velocity v but in opposite direction and sticks to it. Okay. The velocity of the compound body after the collision. So the situation is this is body of mass m moving with velocity v hits another body of same mass moving with the same velocity v. Another body of mass m velocity v. Yes, but in opposite directions and they are going to stick to each other. The velocity of the compound body after the collision v dash is required. So what I can do is that initial momentum should be equals to final momentum. This could be written as m into v minus m into v, because one is moving in positive x, another is moving in negative x. That should be is equals to 2m into v dash, but as it is 0, so this is v dash, so v dash would be equals to 0. Compound body is having 0 velocity after collision. What was your answer? What was it? Was it same? Was it? Are you sure? Great. Let's look at the last question of this session. Which of the following is not, read it carefully, which of the following is not a perfectly inelastic collision? Striking of two glass balls, bullet striking a bag of sand, an electron captured by a proton, or a man jumping onto a moving cart. So which one is not perfectly inelastic collision? Look, when bullet strikes a bag of sand, they both can move with the same velocity, so this would be the correct option. An electron captured by a proton, even they will move with the same speed, they can move. A man jumping onto a moving cart, even this could be the correct. So this one is not incorrect. It's a striking of two glass balls cannot be perfectly inelastic collision, so this would be the answer. I hope this is clear, because this all three are the correct options and they want that we find it out the incorrect option. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Great. So let's just wind it up this session over here. This is all about the elastic collisions. We have started with the elastic collision in one dimension and we have been ended it on the elastic collision in two dimensions. Always remember two approaches. First, momentum is going to conserve. Second approach is coefficient of restitution, which is just the ratio of velocity of separation to the velocity of approach. If we remember these two things, every questions of collision can be done. I hope this is clear. Is it? Great. So let's make many questions based on this. This is very important concept. Even not only in the pure form, it is going to be there in many of the units in its impure method. That means they are not the perfect collisions, they are not just as the question of the collision, but they are used as a multiple concepts over there. Please do it as many questions as possible. In the next session we are going to discuss about the inelastic collision, but before you tune into that, please make sure that you are very clear with the elastic collision. Have Thank you. Have a good day. Take care. Bye bye.